Alright, welcome back to the fifth part of this lecture. Now, I want to talk about another technique or a term that we're going to be using a number of times this semester. We're looking here at a graph that shows, by different databases and so on, temperatures over the last, 50, 60 years or something like that. And unsurprisingly, when you gawk at a diagram like this, you immediately notice that the temperatures have been increasing. But I want you to notice what the y-axis of this scale here says. It says temperature anomaly in degrees Celsius with respect to 1961 to 1990 averages. That word anomaly is what I want to focus on. Temperature anomalies are the difference between the actual temperature and some reference temperature. Like in this case, it was talking about the average between 1961 and 1990, okay? So the temperature anomaly is just how different the temperature is now versus, at a given time than it is compared to that reference temperature, which is typically the temperature over some period, like a climatology, but it wouldn't have to be. Let me give you an example here. This comes from the IPCC report. Here happens to be the June 2009 anomaly. I don't know why they chose June, and I don't know why they chose 2009. But what they mean when they make a map like this is that at every location on the map, they computed some kind of climatological mean temperature for June. So at literally every spot, okay, they don't mean like for the world, they mean literally at every spot on this map, they computed a mean temperature for June, maybe June 1980 to 2009 or something like that. And then they took the temperatures in June 2009 at every point, and they compared them to compute the anomaly, the difference between June 2009 and the average June. So this plot shows the anomalies, the difference between June 2009 and the climatological average at each of those locations. So, for example, places that are in red had temperatures that were well above normal for that location. So in June 2009, the temperature was well above normal in those locations. And colors that are blue, they were less than. And you can see the range over there on that right axis of the diagram there, and you could quickly see how there were several areas of the world that had very large temperature anomalies for June 2009. We're talking something like 5 Celsius. Well, that's about 10 degrees Fahrenheit above normal. That's extremely large. But a huge amount of the world is slightly above that average. But in fairness, what this plot looks like is going to be somewhat a function of what you used as your climatology or your average, that your reference temperature over there, and you would get a slightly different looking map if you had used a different period to compute your average temperatures in June. But it would still be a similar kind of map. It would still reveal the same key features. You would still be seeing most of the planet warmer. You'd still be seeing the main areas where the temperatures are above normal. It's just a slightly different distribution. Why do we use these temperature anomalies? Well, they're actually a hugely important tool in climate science. Absolute temperatures, the actual temperature that you measured at each location, can actually vary quite sharply between one location and another location quite close nearby, depending on the land where you're taking the observations. There can be very dramatic temperature differences between, say, a temperature observation taken in the city and a temperature observation taken in the surrounding countryside due to a phenomenon you may already know about called the urban heat island. Okay, that doesn't mean that there's more climate change at the city than over the countryside or something like that. You would want to compute the temperature anomalies. Both the city and the countryside might be 1 degree Celsius above normal, or 1 degree Celsius below normal, whatever. Another obvious example would be the differences between the temperature, say, in a valley versus at a mountaintop. For example, here I just happened to swipe from someplace a map of temperature observations across Colorado on a particular day. And I liked it because it had these numbers on here. These are the actual numbers of the temperatures being observed on this day across Colorado. And you don't have to really pick and choose too much before you can see places where two stations that are close to each other have wildly different temperatures. I mean, if I just look a little bit over to the right of this little window that I'm in right now, do you see how there's one station that's 16 degrees and just a few miles away there's another temperature that's 39? It isn't like there's more global warming at the 39 degree station than at the 16 degree station. It's clearly the case that there's a difference in elevation between those two stations there. They might both be 1 degree above normal or 3 degrees below normal or something like that, while the absolute temperature, so the anomalies might be very similar, whereas the absolute difference in the temperature might be very strange. Of course, there's no shortage of alarming things to look at when you see a diagram like this one that I swiped from the IPCC report, where you could see that the planet is warming. We're going to talk in a future lecture about how much warming and how we've determined how much it is, and why are there differences between these different archives as to how much what they think the temperature is on any given year and so on. But I think you can agree, again, it's cut off on this diagram here, but whether you believe in those green observations or whether you think the blue observations are more accurate or whether you think the orange observation, they all show the same trend. They just have some differences in how they were computed. But not only are all these different databases showing an upward trend, all the models agree that this is only the beginning. Now, what we're seeing here as we continue across this diagram here is various model projections based on numerical climate models. We're going to be learning about how they are done under different assumptions about our releases of greenhouse gases in the future and so on. And we're going to learn about all the different methodologies, but look at this here. They're all terrible. All of these observations show in coming decades the temperature is only continuing to increase. And this diagram only extends out to the mid-2030s. It gets much worse and more alarming the farther forward you go. Now, what we're going to do with this is, starting on the next lecture, we're going to start learning about what we can do in terms of how do we interpret extreme weather events. When it's really hot one particular day, or there's an enormous ice storm, what can that tell us about climate change? Can it tell us anything about climate change? That's an important question. But we've actually made it now to the end of the first lecture that's actually about content in this course, based on one of the readings from the IPCC report. And before I leave you, I do want you to answer 2 more quick questions that will help you as you check your knowledge and how you prepare for the upcoming exam and so on. Let's look at question 9 here. Suppose the temperature in Omaha today is 5 degrees Celsius. This means that the temperature anomaly in Omaha today is A, 5 degrees Celsius, B, negative 5 degrees Celsius. See, it's a trick question. Temperature anomalies need to be global, not at a location like this. Like I shouldn't be talking about at Omaha. Or D, you would need to know the climatological average temperature for this day in Omaha to answer this question. If this is the first class you've ever had with me, you might not know, but I love to make trick question choices over here in my multiple choices, okay? And expect that things like that will be happening on quizzes and exams. In the meantime, though, let's answer this question by picking one of those 4 options and get a little feedback before you answer the 10th and final question.